So how do we represent codes in algebraic coding theory, and how do we encode any message using the tools we have in algebraic coding theory? For this, we will make some new definitions here. For instance, the concept of a subgroup. Uh, this structure here, the subgroup of a group A is a group, well, it's itself a group, meaning that the addition operation on this set S, which is a subset of A, is associative, and you have an identity element again also in S, and also you have all the inverses of the elements in S within S. Okay, so it's a group by itself, but it's a subgroup of A with respect to addition. Now, a group code, by definition, is a subgroup of the set of binary strings of length n. Okay, with the addition operation is XOR and the multiplication operation is AND. A code is a group code only if for every pair of code words X and Y, X plus Y is a code word. So this is simply the closure property. As long as the addition operation is closed under your set of code words, it's a group code, because then the underlying structure will be a group. Now, since our addition operation is XOR, you have to see that every code word is its own inverse, because when you add any code word to itself, you will get all zeros, which is the additive identity. We also have the concept of a generator matrix. This is a matrix like this one that generates code words when multiplied by the message, the data. For instance, let's say X is my message. Okay, the generator matrix for the even parity code is given here. You take the first element in your message and use it as your first element in your code word. The second element, the third, the fourth, etc., up to seventh. But for the eighth position, you add all the bits up. So this gives you the eighth position, equal to the sum of all other positions. So here this matrix is 7 by 8, because it takes a length 7 string, turns it into an 8-bit code word by multiplying it with this matrix G from right, because I'm assuming this is a row it's a row vector row matrix. So when you multiply it with this, what you get is your code word. Here's the very typical and a famous example. This is the Hamming 7-4 code. The message it accepts is of length 4, and the code words it produces is of length 7. And it's able to correct single bit errors and detects up to 2-bit errors. This is why, this is because the minimum Hamming distance of this code is 3. Okay, so you can detect up to 2-bit errors and you can correct single bit errors. And this is the generator matrix. You see this one, 1 0 0 0. So it takes the first element of the message and puts it in the third position in the code word. It takes the second element of the message, puts it in the 5th position of the code word, and takes the third element in the message, puts it in the 6th position in the code word, and this is the final one. And these three are parity bits. But you see, some of them have missing bits. Okay, so this one is not included in this one not included, this one not included in this one. Therefore, if you have a single parity bit, you cannot know at which position you have the error. But if you have 3 parity bits here, in this case, you will have sufficient information to understand which position was corrupted. A message can be checked with the parity check matrix. Essentially, this is the inverse operation. You produce your code word by multiplying it from right with this matrix, and you check your message, the 7 bit message, which is either a code word or a corrupted code word, let's say, by multiplying it with this matrix, the parity check matrix. If the result is all zeros, then you're in good shape. The code word is a legitimate code word. If it is not all zeros, then there is a mistake. But you will have to find out at which position the error was made. Okay, so of course, when you have a code, this is real life, so you have to implement it, and you would like to have an easy way of doing that. Let n of h denote the null space of the parity check matrix. Okay, so this is the set of matrices of size m by n consisting of elements in Z2, meaning either 0 or 1. Okay, the set of this is the null space, so this is defined as the set of all x's that satisfies x times h equals 0. Okay, so the null space here, you can show that it is a group code. The proof is given here. Since each element is its inverse, I have inverses, and 0 is obviously in the null space. Okay, then I do have inverses, I do have additive inverse. What I need to check is closure. Okay, so you just need to check closure for any x and y in the null space. X plus y, the result of the addition, multiply it with the parity check matrix. Of course, you can apply the distributive property xh plus yh equals 0. Why? Because x is in the null space, y is in the null space. Therefore, this is 0. This is also 0. When you add them up, you get 0. So that means this should also be in the null space. Therefore, this operation is closed under addition in the set. Therefore, this is in fact a group. A subgroup of this group, okay, a subgroup S of group A may be used to partition A into equal size subsets. This is a general definition, not related to the coding theory in general, but this is the concept of what we call cosets. You have a subgroup S of a group A, okay? Let's say you pick an element, then this element belongs in exactly one of these cosets. So what are cosets? A subgroup S partitions the group into cosets. How so? When you just apply the operation in the elements of this subset with the elements of this, you obtain a subset of element set A. Okay, so that is what we call a coset. So you have this, let's say this set, this is A, along with addition, let's say this is a group. And take a subspace of this, let's say this is S, and the identity must be in the subset for that to be a group, because I need the identity in the group. But let's say take an element here and apply the operation with this element and any element in this subgroup. What you get is some subset of the original set. Take another element, apply the operation with all the elements here. What you get is some other subset. Okay, so using this, so let's say, let's take another element, this one. This will give you this exact same subset. So this concept we call cosets. And cosets form equivalence classes. Remember the property of equivalence classes. If two elements are related through an equivalence relation, their equivalence classes are exactly the same. Okay? And if you have at least one common element in the equivalence classes of two elements, then those two equivalence classes must be equal. the same set. Or from the other way around, if two equivalence classes of two elements are disjoint, they have no elements in common, then those two elements cannot be related. So this is the same thing here. If you take two elements, let's say this one and this one, if their operation with at least one of the elements in this set coincide, then they must reside in the same coset. Or alternatively, if none of those coincide, then they must lie in disjoint cosets. So cosets form equivalence classes. Two elements of A, the group here, X and Y are either in the same coset, okay, or the cosets they belong to are disjoint. So this notation is you just apply the operation with X to any element in the subset S. This is that notation. And now the parity check matrix for any block group, any block code, partitions this group into cosets, where each coset includes the messages corresponding to each code word with an error at the same position. So for instance, consider the Hamming code. You have 7 positions in your code word, and actually the parity check matrix belonging to Hamming 7.4 code divides this group into 8 cosets. One of them is the elements that actually has the code words. This means you do not have any errors. All the code words, legitimate code words, are there. Another coset has all the code words that has an error in this position. Obviously, this is a disjoint set from the subset of code words. Another coset, a third one, has all the messages that are corrupted in the second position. Another one has this position, another one has this position, etc. So you see, you have 8 possible cosets, and each coset will give you the position in which the error is present. Okay, so suppose X is a code word, and therefore X times H should be 0 because a code word is in the null space. Let the message be X plus E, where E represents the error. So it's a row vector of all zeros except for a 1 at one single position, representing the error, because it's going to flip that corresponding bit in the message. Now, X plus E times H, this here is my corrupted message. If you distribute this, you'll get X times H plus E times H. But X plus H is 0, so this is equal to E times H. So compute X plus E times H, because X plus E is your message. Either you read it from your storage or you receive it from your communication channel. You just multiply it with the parity check matrix and you obtain a result. If it is all zeros, great, that's the code word. You just decode it. Or if it is not all zeros, you have a list of all these 8 possible cosets and look for which one it corresponds to. Right? It's simple as that. This is what we call coset decoding, and this is implemented in real systems. And a lot of applications have come up from this, and this is used in everyday communications, from like space communications that NASA uses to cellular communications that we use daily. So you see, we have a very abstract theory in abstract algebra, but here we have a very real application in coding theory.